no one's done that kind of process engineering before. Like, how do you actually develop a process that enables you to...
What intensity of energy are you using? What did you say?
Somewhere in the range of like 1,000.
But like, why do you need that much energy to be shifted? This is just like, that's how the math works out when you need to shift that much energy to a drone?
To actually control the radiation access level, which is kind of like the key metric that enables you to...
The idea that like if someone walks through the beam, the safety beam picks them up first and then you just turn it off.
I definitely disagree that we should radically focus on the cells and the transmission. I think around 2,000 kilometers of range without too much loss.
Is there anything you've done on the thermal management side that's been interesting or like a bit different?
There's so many problems to solve in actually scaling, like outside of invention, the pure capability, and those are often underestimated, I'd say.
Do you think the other impacts on efficiency are that important? For example, like attenuation from the weather environments and things like that, or do you think they're negligible to the point where it's just like...
Dive into the intriguing world of deep technology and its intersection with business on Technocracy. We're your hosts, Ajay and Loon. Let's explore the breakthroughs and people shaping the future of technology. Technocracy Podcast.
So you get comfortable with it, right? Yeah, tell the story, but we may not include it.
Yeah, absolutely. So one of the first things I did when founding Aquila was actually writing up the Constitution. And I actually have it here. So the original Constitution was like, Aquila, the company shall be named Aquila. And the reason for this is it sort of envisions an eagle stretching her wings and taking flight on the glowing band of the Milky Way. So that's like where the eagle constellation of Aquila is positioned in the sky. And for us, the eagle represents humanity, while the glowing band is like the light on which the eagle glides. So it communicates this mission of like sort of uplifting humanity through light. And that's the kind of symbolism that really appealed to me. Yeah. So, you know,
did you actually think about all this when you did it, or did you just like name it and then like come up with a reasoning afterwards?
No. I mean, I guess it was a bit of both. Like so I was, you know, really interested in space, and I wanted to name the company about something to do with space, and then sort of looking through like all the different constellations of Aquila from like a symbolic perspective just appealed to me. Like even in that original Constitution, it's like, okay, we're like, the reason we're here is we want to create a wireless energy transmission system with infinite scalability, and this will enable us to build the infrastructure that enables expansion into deep space and ultimately unlock the sort of infinite wealth of the cosmos to help improve lives. Like that's kind of, you know, and I have like that other note there, which is like, okay, we're here to advance humanity. Any situation where there's in the pursuit of profit are mutually exclusive. We need to choose the advancement of humanity. So like there's a lot that sort of a lot of thought that went into, I guess, what type of company I wanted to build even before really starting, which was, I guess, a bit of an unusual trajectory to take.
Yeah, it makes sense. It's interesting that you're thinking that far ahead, because I guess like one common thing would be the fact that like what I thought was interesting is that 99% of our data is transmitted like under the ocean as opposed to like through satellites, right? And so the thinking here is that like, oh, like what if we just find like a room temperature superconductor and just like do it under the oceans instead of like beaming it through space? But I think what's interesting is you're thinking about like a multiplanetary civilization and like thinking about how do we mine an asteroid and things like that, right? Which is where you're required, right?
Yeah, I mean, I think it's kind of obvious to me that you need this type of laser energy networking to enable expansion and sort of operations into deep space, because like you just need a lot of energy to go really quickly, and you need the infrastructure that can provide that energy collimated over long distances. And really, the only technology that is going to enable that is optical sort of power beaming. So we do see. So obviously, there's like an incredible number of important problems that we're solving on the trajectory to that sort of vision of a future where humanity kind of beautifies the entire galaxy and starts expanding throughout the universe. But you know, we do see like the technology is ultimately leading to that point, I guess, if that makes sense.
Yeah. So quick introduction for those. I don't know when we're going to tune this in, but like, let's say we start now. Quick introduction for everyone listening. So Billy is the founder of Aquila. We have talked about this company in like one of the first episodes that we did. And I think the takeaway was that like we weren't sure on the efficiency side of things. We just thought it was a very inefficient system to transfer energy. And then we weren't sure about the incumbents or the alternatives of like, underwater cables and superconductors and things like that. So we sort of left it as like, okay, unsure. However, I think what's really interesting in the last year or two, just watching you guys from the sideline, is like, one, the efficiency gains you guys have made is pretty sick. Yeah. And two, you've actually found, and I think most companies actually start this way, you found a niche that like requires your technology. There's like no way to do it otherwise, which is the drone stuff, which we can talk about. And then you can kind of expand from there. And also, I think just as you were talking, the longevity of this, like the 100, 200 year vision is really interesting, right? Yeah. So that's something really exciting. How important is that vision for the hiring process? Like, are people thinking about the multi-planetary thing and like the 100-year vision when joining your team, or like what's been the pitch so far?
I think, my job as the CEO is to sort of work across every time scale. So I keep the vision in mind, and I have the set of metrics that we track around effectivity, so speed, power, and distance of transmission, efficiency, cost per watt, and then the idea is we scale the effectivity, we sort of drive down the cost per watt, and we sort of increase the network scale. And over time, we drive this kind of flywheel that unlocks larger and larger scales of applications, and eventually leads towards that long-term vision. But in terms of hiring, I think the important thing is that everyone's aligned with the mission, and the mission is kind of like this infinite thing, which is empowering the future with an infinitely scalable energy network. So that goes from drone networks all the way to, arbitrarily far. It's something that we can never really achieve, but people have to be aligned with that. It's like, okay, we exist to empower the future. We exist to sort of uplift humanity in some sense. And everything we do is kind of feeding into that mission. Obviously we're also, aligned with the values. So we look for people who have this kind of pessimistically optimistic outlook. So it's like, okay, if we
so engineers basically,
engineers, there's all these problems, but like there's something cool that we're building here, and it's going to create a lot of value. We look for people who are stewards, so they steward their community, they sort of care about the environment. We look for people who are ultimately authentic and can communicate authentically in a sort of radically authentic way. And the other thing is we just look for people who have demonstrated that they can grow and sort of continually change as a person over time. Those are like the kind of high level things that we look for from like a values and mission perspective. And then, role by role, we'll have a lot of technical competencies we're evaluating.
What's the transition been like? So you started off by beaming energy to like a moving target, right? That was, I think, the very first demo. It was just like you had this drone and you were trying to beam energy to it and make sure that you could actually hit the target and transfer some energy. This has obviously scaled over time with experimentation, and now you're trying to move from an R&D phase of beaming energy to an operational readiness phase. Yeah. And I think the first pilot you're doing is a drone, like a Sentry that's sort of monitoring the coast of a country. What's it been like transitioning the company, the team, and the way you build things to something that's a little bit more production ready?
Yeah, quite difficult, I'd say. So just like giving a bit of history, like you said, the first demo we did, it was a drone in the lab. It was flying above the transmitter. It was about 1 meter above the ground, and we were transmitting about 20 milliwatts of power. More recently, we've been doing 2 kilowatts over basically 400 meters, and we can technically do a lot further than that as well. But those are the current demos we're doing for national security customers. I'd say like when we started, it was interesting because like we initially hired a bunch of PhDs, so there was like mostly PhDs on our team. I was one of the few non-PhDs, so it was very like research kind of focused because a lot of the risks that we needed to retire were deeply technical and kind of research focused. So that made sense at the time. And then we sort of shifted towards, okay, given the underlying optical and photovoltaic technology, can we build the sort of operating layer around it? So the targeting systems, the sort of laser locking procedures, the sort of safety monitoring, and like all of those layers are going at, different layers of speed. So you got the targeting at like, a couple hundred hertz, the laser lock at 110 kilohertz, and then the safety monitoring at 10 to 100. So you're able to have like this really fast performant engineering layer built around the actual underlying optical power beaming. And that enables you to not just like enable the delivery of power optically, but also enable, precise power delivery with like safety and sort of compliance with regulatory standards. So as we were building out that so those elements, we kind of shifted towards more mechatronics, electronics, various kind of early career engineers. And more recently, as we've shifted towards productization, it's been about bringing in more experienced people who have, done this type of stuff before and can take a product to market. So it's really just been about shifting how we're hiring and sort of the composition of our team over time.
How big is the team now?
16 people.
Okay. That's fair.
Oddly enough, though, so we were in New Zealand kind of before this, so we shifted everyone to Sydney, and at the time we were like 12, so this was like August last year, and then we lost basically half our team, and then got down to 7 or so, and then sort of grew back to 15, 16 very quickly. So it was a bit of a tumultuous period.
Was that because you like recomposition to meet company goals sort of thing?
Pretty much. I mean, It was like we got a new sort of space with a lot of testing infrastructure, again, aligned with that productization kind of objective. We needed to collect a lot of data about the systems. We needed to prove that we had sort of the ability to comply with these regulatory standards for like unrestricted operations in the market. And we needed to shift towards more of a productization team composition to sort of empower that. There's just a lot of sort of change across the board as we were going through that transition.
To be fair, I think with most companies within the first 2 to 3 years, the churn rate is extremely high and it sort of stables over time. And there's a few reasons. I think one is like, as a founder, like you don't actually know what you need until you get there. Like you think you need X, but you actually need Y by the time you get there. And then also I find culturally, the kind of people that want to work from 0 to 1 sometimes don't really enjoy the 1 to 10. It's like a different sort of journey. So yeah, I just want to reassure you that like, I think this is a normal thing that happens with most companies.
Absolutely.
Let's move on to the tech side. So there are so many things you're doing, right? Because there's the speed of delivery. There's the laser locking system where you actually have to aim it, which is quite difficult. You have to manage the heat and safety side of things. You have to scale the distance you can actually beam something, and then also the efficiency of the transfer. What's actually the hardest part, like out of those variables that you found?
Yeah, this is a good question. So at a high level, we've tried to minimize the amount of invention we're doing, because invention, especially of new like science and discoveries or whatever, is extremely risky from like an engineering perspective. So for the most part, we've focused on that sort of operating layer and like how can we best integrate what already exists and sort of build the systems on top of that enable the productization and the operations of these types of power beaming systems in the market. And I guess my initial intuition was, hey, if we can just focus on that operational layer, we can abstract away a lot of the complexity of building these types of systems. And that turned out to be totally wrong. And actually, the integration, the process engineering, like just one example. So with the cells, we sort of revamped our cells a couple of times across the history of our company and took the efficiency from like, on the order of 1% up to 40% now. And every single time we had to like integrate something that was more and more cutting edge, and like the performance requirements were like more and more extreme. And most recently, we're talking about basically 1,000 suns equivalent of power through like a sort of 50 by 50 millimeter aperture. And then you have to dissipate all that heat away because like you have to keep it at like 60 degrees or so. So you got the extreme kind of electrical density that you have to integrate into, a power system that then charges the drone. And you've got this extreme kind of thermal discharge requirement. And those have to be working all at once, which is actually very difficult from like a materials perspective. Like no one's done that kind of process engineering before. Like how do you actually develop a process that enables you to integrate these materials and this like intensity of like power sort of input, but also like thermal dissipation, like all in the same system. And it's extremely challenging to do. So I'd say receiver.
Wait, what intensity of energy are you using? What did you say?
So there's about 2 kilowatts of optical power going into 50 by 50 millimeter sort of aperture.
Okay.
It's somewhere in the range of like 1,000 suns equivalent. So imagine 1,000 suns shining on like a sort of small aperture at once and trying to like dissipate all that heat, it's pretty challenging.
Yeah, that's insane. But like, why do you need that much energy to be shifted? This is just like, that's how the math works out when you need to shift that much energy to a drone.
Yeah, I mean, you want to have, so again, like from a product perspective, you want to have a small, compact form factor sort of receiver that can receive a lot of power, charge the drone without like impacting the operations too much. So there's product considerations here. There's also actually, like, again, from that operational perspective, there's safety considerations. So it turns out we want to have a very tight sort of compact power beam, which is surrounded by a more kind of diffuse safety beam that's kind of monitoring and ensuring lock, ensuring there's a clear pathway all in this sort of one system. And to actually control the radiation access level, which is kind of like the key metric that enables you to deploy these systems unrestricted in the market, you have to have the power beam be very compressed and the safety beam be quite diffuse by comparison. So like all of those kind of requirements just like drive you to have to really innovate in terms of the performance and the compactness of the system.
Is the idea that like if someone walks through the beam, the safety beam picks them up first and then you just turn it off?
Exactly. And the key kind of requirement there is that in any kind of reasonable or reasonably expected scenario, like the safety system is going to pick up the person and shut off the main power beam before like the person can be exposed to a dangerous level of optical radiation.
Yeah, makes sense. Because there's still impact even if they're near the beam as opposed to just getting, cut through by it.
Yeah.
Right?
So to like get a bit technical, the beams we use are Gaussian. So they kind of dissipate around the edges and the radiation gets very low. It sort of goes away exponentially, but there's still like a big tail, especially when you're dealing with like an extremely intense, powerful beam. There's like a pretty large tail where there's like a pretty dangerous level of radiation. So you have to ensure that entire region is just protected by what's called a virtual protective housing. It's kind of similar to like, okay, if you look at, for example, laser manufacturing systems and the way they kind of build those, they have like a sort of material housing built around the manufacturing jig. That means that the material housing kind of protects the external environment from like any radiation that's kind of intense radiation that's happening within the sort of housing. In our case, what we've got is basically like a virtual protective housing, which does the same thing, but like with a virtual kind of sensing layer built around the main power beam.
Interesting. Okay, that's cool. And then I want to shift gears to the efficiency side of things, right? So I think one of the coolest things is you almost 10x the efficiency that you started with, right? I have two questions actually. One is like, what has been the big critical engineering breakthroughs that have helped you get there? And what do you think is like the biggest limiting factor preventing you from getting to 100%?
Yeah, absolutely. So I guess like the two questions, I'll tackle the first one first and sort of get on to the next one. So with the first question, the real unlock that we've had over time has been basically shifting the cell architecture and sort of having the cells more tuned towards a particular frequency of light. So with a solar panel, the core problem with a solar panel is you're trying to like capture essentially every type of radiation from the sun and convert it into electricity. And it turns out that a solar panel is designed mostly just to sort of capture one frequency of light, but then it's sort of inefficient at all the other frequencies of light. So in total, that means that the efficiency of a solar panel is it's difficult to get it above like 25 or so percent. With us, we have the advantage that we only have a single frequency of light because we're dealing with like lasers. So we can tune the PV cells to like that frequency of light. So initially, when we were just doing the POCs, I literally got like a bunch of solar panels, just small ones off of eBay, and we had like a 980 nanometer laser. So it was like kind of below the silicon kind of band gap or the energy at which. So the photons of light at 980 have more energy than the silicon band gap, which means that you can actually transfer power optically at that frequency to like a standard solar panel. So that works for like proving out the concept, but it was like pretty inefficient. And then like we sort of shifted towards 1080 nanometer light. And the reason for that is we wanted to start integrating these really high quality sort of low cost systems at 1080, because that's where like all the amplifiers are for fiber laser manufacturing. So it turns out that you can get very low dollar per watt, very high beam quality systems, and that kind of enables you to have compact sort of delivery of optical power over very large distances. So super important for us. We wanted to shift towards that frequency, and with the silicon band gap being at about 1100 nanometers, and with the sort of frequency we're dealing with at 1080, like it was just very challenging to like couple that to the actual silicon cells, and the efficiency was like super low. And then we shifted towards these what's called these 3.5 semiconductor cells, and what you do there is you actually have a semiconductor alloy. So you have like different forms of material. Usually we're using indium, gallium arsenide, and phosphate. And you vary the composition of the material to kind of change the semiconductor band gap. So with that, you can actually tune the band gap to match it to like whatever frequency of light you're sort of wanting to couple to. So that enables you to get like really high efficiency. Like these cells at a base level are between 50 and 60%. And in terms of like conversion of the incoming photons of light into like electricity, sort of activating the electrical sort of jumps across that band gap. So those were like a lot of things we did, and the like even from the perspective of the 3.5 cells, they were also like what I call vertical multi-junction. So that means you sort of stack a bunch of layers together. It means you can absorb much more efficiently and at much higher voltage, so you can get a lot more volume of power through the cell. So there's like all these kind of little tricks that you sort of need to deploy to beam power at like such high optical intensities. And then you need to actually get that into the drone power bus. It's like the sort of process engineering around like, okay, let's integrate these cells into like the module. Let's couple the module to like what's called a maximum power point tracker. And that needs to be working at a very high frequency, because like the light that's coming in is varying a lot in like a short space of time. Because it's just like, it's not like the sun where it's like really constant. It's like more of a kind of beam that's sort of shifting around. So that sort of process engineering is difficult as well. So like there's all these kind of steps that you need to take past that. And like at every step, you're getting losses, but you can kind of optimize those losses to be less and less, so you can drive that efficiency up over time. And like through that process of iteration optimization, we've been able to go from something like 4% to more recently 40%. And we're definitely not at the limits of what's possible just yet. In terms of the limits of what's possible, so the cells themselves, the limiting factor is what's called the thermalization. And that's also kind of addressable, because like essentially with a particular frequency of light, you've got a particular limit as to like how much of that can be converted into electricity and how much can be converted into like thermals. And that's kind of just quantum mechanical in nature. It turns out you can also get a lot of that thermal energy and convert it into electrical again via sort of thermoelectric converters that can be attached to the cells. But in terms of the thermalization limit, it's around 70%. So you can get these cells to about 70% efficiency with a thermal sort of converter, potentially 80 or more percent. And then on the transmitter side, the diodes are getting to 60, 70% now. Potentially even 80%. So, if you've got a all semiconductor kind of solid state system, so there's these new innovations around like photonic crystal surface emitting lasers. And these are basically like full kind of semiconductor systems that can sort of amplify and also like produce the light on chip. And these can be at around 70 to 80% efficiency. So we definitely see it as possible to get like full kind of end-to-end efficiencies around 60 or so percent. And that's kind of what we're going to over time.
Okay. That's awesome. That's super interesting. Do you think the other impacts on efficiency are that important? For example, like attenuation from the weather environments and things like that? Or do you think they're negligible to the point where just like, radical focus on just the cells and the transmission is like the important part?
Yeah, I definitely disagree that we should radically focus on the cells and the transmission. I think like my perspective is that like actually deploying these types of energy networks at scale is like almost fully an operational problem. And like the underlying technology is going to keep improving exponentially over time. That was kind of the thesis with Aquila of like, okay, you've got grid systems which are getting exponentially slower and more costly to build, whereas like optical technology, because like all these semiconductor cost curves, is getting exponentially better, faster, cheaper. So like project that forward, and obviously there's going to be a huge amount of disruption in the space. But like the challenge is like operational. So like building up that operational capability and sort of scaling that. And so that's what we tend to focus on. I think in terms of the attenuation itself, so at sea level, you're talking about maybe 50% loss over 20 kilometers, because you've got like the attenuation coefficient kind of works out to be that much. And then so like it's definitely not tenable for like very long distance at sea level, but fortunately there's a lot that you can do to extend the range. So we actually have a plan in the relatively near future to deploy these stratospheric drones. It's like for us, power isn't a constraint because we can deliver power up to the drones optically, which means that we can have like a fleet of stratospheric drones that can essentially service like an area 24/7. And through the stratosphere, it turns out you can get around 2,000 kilometers of range without too much loss. And with these types of drone fleets, we could say shift energy from like a population center to like a range of remote locations that require power. So for context, there's about 1 billion people in the world who have unreliable access to electricity. So they essentially don't have a grid connection. And by like sort of extending and improving energy distribution through these optical networks, we can really bring energy security to those people among like a bunch of other applications. So like even in the near term through these like, relatively short range applications, there's a lot of value that we can provide.
Yeah, it makes sense. Yeah, it's like satellite Wi-Fi, but energy essentially. We actually did. We bought a few Starlinks when we were doing our business in Nigeria because like it's just hard to get reliable internet. So we just bought that, and I could totally see a world where if you said to us like as a company like, hey, pay us like X amount of dollars per month, and we'll make sure that your stuff doesn't go down. I'll be like, hell yeah, let's do it. So. Yeah, that's super interesting.
That's right.
How do you think about jumping back to like the heat stuff? Like, is there anything you've done on the thermal management side that's been interesting or like a bit different?
I think, there's, again, like I very much try to avoid doing research or like things that are too different left of field. I think what we focus on doing is like being incredibly operationally excellent at like integrating what already exists. I mean, that said, we have pretty unique kind of materials for like our receiver. Like we've got a thermal paste that on one hand is like extremely thermally conductive, but electrically insular. So like we don't get loss through the substrate of the electricity. So like there's all these different like materials and the way we've integrated them to like kind of control the thermal and electrical flows that are definitely quite innovative. But I think, we try to avoid doing any kind of invention or new science. We try to sort of stick with what works and just be like totally operationally excellent at integrating and sort of developing on top of that.
Makes sense. But like, for example, I think you said you're manufacturing your own cells now, right? Is that purely because like you just can't find a partner that's manufacturing the way you guys need it?
Yeah, I mean, there's definitely a lot like that. I think when I started out, I thought that we could just like,
off
the shelf everything. And it turns out that when you're dealing with cutting edge hardware, where like no one's ever done like anything within an order of magnitude of what you're trying to do, it's like turns out you need to do a lot of stuff custom. We sort of we do outsource the manufacturing, so we don't, obviously it is like custom chips and whatever, but like we don't do a lot of that in-house. Potentially over time we'll start building more in-house capability, but for now, like most of our resourcing objectively is into the operational sort of element of optical power beaming.
Yeah, I have, I guess, 2 more technical questions, and then I kind of want to just talk about vision stuff because I'm curious to see how you see the future. So one is like, I guess, like what have been the challenges around scaling distance in terms of like beam shaping and alignment and stuff? And then I guess like how exactly are you doing lock-on? Like are you using some sort of automation? Are you using AI? Like how are you actually doing that stuff?
Yeah, absolutely. So scaling distance, like from an optical and power perspective, has been like really challenging. again, like there's so many problems to solve in actually scaling, like outside of invention, the pure capability, and those are often underestimated, I'd say. Scaling distance, like just beam shaping, like alignment of the power and safety beam, sort of collimation over distance, sort of even like effects like atmospheric kind of aberration and sort of these different atmospheric effects you get at different wavelengths, and sort of controlling that from a safety perspective to ensure that under most any reasonable scenario you can still guarantee that the system is safe has been definitely quite challenging. And then we're dealing at like incredibly high optical powers and sort of power density, so like we have to have optics that can with a relatively compact form factor as well, just like beam this amount of power continuously in like a super compact and power dense like form over distance, and like not sort of lose collimation. Like there's so many mechanical optical, like those mirrors are what's called a tuned dielectric, so they're something like 99.99% reflective within like a tight wavelength range, so like you don't get a lot of heat load through the system. It's like pretty efficient, and then you have to like ensure that they stay kind of locked in place. Definitely a lot of process engineering around like scaling distance from like an optical perspective as well, which is cool. In terms of like, I guess the operational element around that core optical capability, like we use several layers of targeting, and we tend to take the approach of just run the system really fast, and that kind of solves your control issues and ensures precise kind of consistent delivery of power. The actual
what does that mean exactly?
So
what do you mean by just run it fast and it'll work?
Yeah, I'll explain that a bit more. So there's actually a bunch of layers to what we do. First is like the sort of GPS and kind of initial signal kind of target acquisition, and that tells you roughly where it is in space, and then you can kind of point towards that with the camera system. The camera system has like a filter. It's able to pick up on these IR LEDs. It's pretty simple. It's just like like there's no AI. It's just like pure software, but it runs that at about a kilohertz. So you're again like it's a very fast kind of estimation of the position back to the sort of targeting system. And the targeting system can use that to run these motors that are sort of very precise in terms of like being able to target in space precisely at around that speed. Once you have that kind of acquisition, then you need to run the sort of secondary systems, which are on one hand there's the laser locking, and on the other there's like the sort of safety monitoring. So the laser locking sends out a piloting signal, which is at 1550 nanometers, which is an eye-safe kind of laser wavelength. It's very low intensity, so it doesn't have the potential to do any damage, and that kind of gets a signal back from the receiver. If it's locked on target, it gets a strong signal. If not, then it doesn't. Interestingly enough, so when I look at a lot of the systems in our technology stack, like most of it wouldn't have been possible until quite recently. Like one example, even on the receiver side, dissipating the heat load that we need like what's called a 3D vapor chamber, and those kind of got built up because of like extreme thermal requirements that are coming about in data centers. Then on the transmitter side, with the laser locking, we actually need to run a neural network very quickly to estimate the offset of the actual drone from like essentially target lock, and that we need to run on a neural processor, and neural processors didn't exist until like basically end of last year. So like that wouldn't have been possible until recently, but the laser locking kind of enables you to then ensure that you're exactly centered on target and the energy is going to go where it needs to be going. And then we send out a low power kind of piloting sort of stage of the power beam just to sort of gauge the distribution of power on the cells, make sure it's all aligned. And if the pathway is all clear, then we can start sending through the high power beam. So that's like the sort of laser locking is running at 10 kilohertz. The safety sensing is running at like on the order of 100 kilohertz. They're running super, super fast. And that means you have a lot of precision in power delivery and a lot of reliability in the safety sensing as well. I think there's actually a few more things I want to mention here. So in terms of like this wouldn't have been possible until recently, there's like a couple of reasons why. One is the OPC technology. So like the type of architecture that enables you to convert optical power at like really high intensity, which you need from like a safety perspective, didn't exist until recently. The other is what's called the automatic emission control standard. So it turns out the IEC, which doesn't necessarily regulates, but like creates standards around laser product manufacturing. There was no standard for declassing free space systems until the AEC, which is set for release end of this year. Aquila's actually a member on that committee. The AEC essentially says, look, if you can control the accessible radiation in free space through like this virtual protective housing, which we do through our kind of laser locking system and safety monitoring, then you can say, okay, from like a radiation perspective, like the power beam is really dangerous, but that radiation isn't accessible. So like the access level in terms of like the danger pose is much, much lower. And that enables you to then sort of deploy these systems in the market. So again, that didn't exist until quite recently. And the other is of course, like just the cost curves in lasers. And that only came about because people were deploying these systems for like scaled sort of laser manufacturing operations, and that drove down the cost, increased the quality. So we've seen something like 3x year on year single mode power scaling in the underlying sort of 1070, 1080 nanometer laser systems, which just like drives the dollar per watt down and like massively improves the capability in what's actually possible in, I guess, the optical power space.
Wow. I think you're onto something when you like literally don't have rules for what you're doing yet, and you're like coming up with these rules with other people.
Yeah.
I also don't know a startup that's hitting so many different aspects of engineering at the same time. Like you're doing laser stuff, you're doing software engineering, you have material science, and there's so many different aspects you're doing. It's quite unique in that regard. It sounds quite difficult. I'm glad I'm not the one doing it, but I'm glad someone is doing it.
Yeah, it's very challenging.
On the vision side of things, so I actually want to hear from you, like, what does 12 months look like? What does 5 years look like? And what is, I don't know, give me some really long time frame. I don't know if that means 20 years, 10 years, or 100 years, but like, I want to hear what these look like in your head.
Yeah, absolutely. So for 5 years, I'd say, we've got these systems on the field. We're starting to, we've developed these networks for national security customers for integrated base defense border security. So mostly just like monitoring applications. So we've started deploying the scaling. We've built on top of this like initial application space what's called we call a sort of open integration layer. So the idea is, look, obviously there's these initial high value use cases we're targeting, but we see that wireless energy networking is a very general purpose platform technology. So we want to give people the tools they need to build a successive kind of number of applications on top of that layer. So we'll see in 5 years people starting to integrate these networks into a wide range of applications and use cases. In 10 years, I'd say we'll start to see the electrification of the aerospace sector. So first dominoes to fall will be kind of direct point-to-point freight. And for context, today there's a lot of very inefficient distribution routes where like it's too costly to sort of run a 747 with like 110 payload from like one location 200 kilometers to the next. And then like the truck networks are just like incredibly costly as well, because like you've got like this like wide range of networks you have to serve, and the routes are just complex and sort of time consuming, and you've got like the labor, you've got the fuel. It's just like it's very uneconomical from a trucking perspective as well. But if you have like direct point-to-point routes where you can run like kind of mid-range drones, so like drones that are able to carry say 100 kilograms of payload, and you can go point-to-point, then that starts becoming much more economical. So we'll start to see an electrification of the aerospace sector, starting with freight and sort of more heavy-duty electric drones. And eventually,
so Amazon just delivering parcels like from one country to another, basically.
Something like that, yeah.
Or same day delivery from Singapore to Sydney, basically.
Yeah, I mean, like once you can do this, obviously it unlocks like a lot of same day delivery opportunities. And the general trend in logistics is towards more point to point, more direct and sort of faster. So like it really unlocks a lot of opportunities there. And then 15, 20 years, I'd say, we'll be sort of connecting billions of people to energy security in terms of like bringing optical power connections to like all these remote communities and remote sort of operating sort of areas, like, you know, maybe it could be military or sort of mining, but like that's going to happen through these kind of stratospheric drone networks. And then 2020 to sort of 30 is really about scaling and sort of connecting the world's energy system together, and being able to shift power optically through space from, say, like outback Australia to like power factories in Europe or sort of peak hour in New York City. Like all these kind of applications will become possible over time as we really drive the effectivity of the network, so the speed, power, and distance. We increase the network scale, so the throughput, and sort of drive down the dollar per watt. So like, you know, all of these are kind of correlated with specific targets in terms of like what metrics would be required to unlock these markets. And we think that based on the current exponential trends, like we'll see, you know, a lot of this happening within the next 10 to 20 years.
Do you think there's a world where you start looking at like, I don't even know if this is possible, but like more last mile delivery of the electricity? So like if we can access Wi-Fi on our mobile phones, like is there a world where you can transmit energy last mile as well?
I mean,
in some
definitely.
sense?
I think it, of course, like it's definitely possible, and I think it will happen over time. I'm not sure about like what the market is for that just yet. Like I know we have a lot of you know, really valuable markets that we're tackling in these like, you know, areas around aerospace, and from a sort of, you know, you need to build a company that provides a lot of value to drive a flywheel to sort of unlock all of these other sort of developments over time that makes sense to focus in that area. But I think last mile is definitely something that will happen over time as well.
Yeah, it's interesting. I feel like there's definitely a market for like, you know, you saw people in San Francisco and say like, hey, your phone will never die as long as you're in the city. Like, I think there's probably a market like $500 a month or something like that. What people would pay it.
Yeah, absolutely.
Yeah, this space is super interesting. I'm curious to see where it all goes. If people want to learn more or like check out your stuff, like, do you write? Do you publish anything, or where can they check out more stuff?
Yeah, I mean, outside of Twitter, not too much. I mean, I'd encourage people to go to our website, www.aquila.earth. In fact, within about a month, we'll be sort of revamping the entire website, and that's going to show a lot more details about our product roadmap, which is, I think, quite exciting as well. So that's cool. And yeah, I mean, I'd say like I probably am most active on LinkedIn out of everything else. So connect with me there, and can sort of go from there.
Awesome. Thanks so much for your time.
Absolutely. It was my pleasure.